Hello, my name is Perry Roderick, and I'm going to be talking to you all about the vapor compression refrigeration cycle, also known as a heat pump. So here you see two of the common heat pumps, an air conditioner and a refrigerator. These are two of the most common ones you'll see in the world. So the objective of the experiment is to learn how to perform a thermodynamic analysis of a heat pump, also learn how to measure the coefficient of performance of the refrigerator and a heat pump, and describe the vapor compression refrigeration cycle in the pH diagram. So here you can see the basic cycle of a heat pump. There's four main components. First we have the compressor, which will compress the refrigerant to a higher pressure. This it increases the pressure and then also increases the phase change temperature. So that increased phase change temperature will allow it to dump heat into a room temperature environment. Next we have the condenser. So the condenser is where the heat actually gets dumped. The state will change from a vapor to a liquid as the heat is being released. And this is like the coils on the back of your refrigerator. Next we have our expansion device. The expansion device will decrease the pressure. This will decrease the phase change temperature, which will allow it to absorb the energy from that low temperature environment in your freezer or refrigerator. And finally the evaporator, which is the coils inside the actual freezer or refrigerator on the low temperature side. So this will absorb the heat and the refrigerant will turn from a liquid vapor mixture to a vapor. Here we can see the process on the TS diagram. So from 1 to 2 is isentropic compression. This is where electrically pressure is added to the system. Then 2 to 3, it follows that constant pressure line. This is where heat is dumped into the warm environment. Then 3 to 4 is our expansion valve. This is where the pressure drops. And then 4 back to 1 is where the heat is absorbed from the low temperature side. So the difference between the real and ideal cycle, the ideal cycle would ideally be isentropic for 3 to 4 and 1 to 2, but in the real cycle it's just not possible. We're going to lose some entropy. So an important part about the heat pumps is the thermostatic expansion valve. This thermostatic expansion valve regulates the flow of refrigerant through the system. So this is located right before the evaporator, and this sensing bulb on the thermostatic expansion valve is located after the evaporator, and it's filled with refrigerant. It's connected to the piping, and it'll be around the same temperature as the refrigerant after the evaporator. So whenever the refrigerant it's designed so whenever the refrigerant gets to too high of a temperature, it'll actually start evaporating itself, and then it will flow through the capillary tube into a diaphragm. So whenever the heat gets too high, it will actually open the valve, allowing more refrigerant to flow through, which will allow it to get back down to a lower temperature. And then when it gets down to that lower temperature, the refrigerant in the bulb will get back down to a lower temperature and it will close the valve. So it's a self-regulating system, and it's designed based on the parameters that the system requires. So we get our coefficient of performance from the pH diagram. So the difference between the coefficient of performance for a refrigerator or a heat pump is the difference between, for the refrigerator, we're going to use QL to get the coefficient of performance because we want to look at how much heat is being removed from the system. So that'll be the enthalpy at state 1 minus the enthalpy at state 4. But for a heat pump, we want to look at how much heat it's putting into the system. So that'll be, at the top, it'll be the enthalpy at state 2 minus the enthalpy at state 3. And then for our expected results, we go back to thermodynamics. We have, at each state, we have a few knowns, and we can use those and the tables for R134A to get the enthalpies at each state that we need to calculate the coefficient of performances. So for state 1, we have the temperature and the composition, and so it's a saturated vapor. So we can go to the tables and get our H of 235. At state 2, we know the pressure and the entropy. So we can get our enthalpy at 275. At state 3, we know the pressure and also that it's a saturated liquid, so we know the composition is 0, and we can get our enthalpy at 99.56. At state 4, the temperature is constant, so the temperature line is constant, so then the enthalpy is equal to the enthalpy at state 3. So we could plug this into our refrigeration formula and get a expected coefficient of performance for a refrigerator at 3.41. For a heat pump, I believe if you just add 1, you'll get the coefficient of performance for a heat pump. They're just kind of reverse of each other. And that's it. Are there any questions?